All right, so this is an example that kind of in a different way breaks down these problems. So I kind of wanted to show a method, or show the method that more or less did both. And what I mean by both is, I mean using the tool that we use, but also showing kind of the shortcut, or a way that requires less computation that we can get the same graphs. So one of the first steps is to simply identify these three things. The amplitude, there's actually another piece to that we are going to take a look at. But first, just kind of taking a look here, we can see that the amplitude of this graph is going to be 2. We find that by taking the absolute value of A, which is just 2. But I want to take note that the negative means that we're going to flip. That tells me that I'm going to flip my graph. And I'll get into that a little bit more in a second. But it has to do with the traditional shape of a sine curve. Now, for the next piece, I want to look and just get an idea of how I'm going to shift vertically. Now, the vertical shift is actually pretty easy. It's just whatever you're adding or subtracting to the entire function. So not inside the sine function, but if we basically took this as being the entire function, or trig function, then we're just going to add 1 to every value that this spits out. So I'm going to say that I'm going to have a vertical shift, and I'm going to go up 1 in this case, because we're adding a 1 there. So that takes care of the first two pieces. The next piece is going to tell me basically two things. It's going to tell me my horizontal shift, so it's going to tell me how much I go to the left or right, but it's also going to tell me basically how much my period is going to change. In other words, it's going to tell me how much I'm going to go from the left to the right, or right to the left, and it's going to tell me how skinny my graph is going to be, or how wide my graph is going to be. You can almost think of an accordion when you think of these trig functions in that way. Now, there's a couple ways that you can actually find this piece of information. The big one is, the easiest way is that there actually is just a formula that you can memorize. And the formula is that we take C, which is this term right here, and we divide it by B. Now, keep in mind that C, when you say C in this case, you're actually going to, the actual formula is Bx minus C. So even though there's a subtraction sign in front of the pi over 4, that actually means that C is positive in this case. So we would have a B equal to 3 and a C equal to pi over 4. Which makes sense. When we looked at functions similar to this before, we knew that we basically did the opposite shift. So if this was negative, we'd shift pi over 4 to the right. It's going to be a little bit different for this one, but we can think of it in a similar manner. Now, what we can do here is we basically would take, and as I said before, the phase shift is just C over B, which in this case would just be pi over 4 over 3. Another way of looking at that is pi over 4 times 1 over 3. So now I know that my phase shift here is actually pi over 12. And that tells me a couple different things. But one of the big things it tells me is that my starting point will no longer be where it is. It's basically, this means that I'm going to shift pi over 12 to the right. And so far I have quite a few good pieces of information. And now that I think of it, the period change part of this actually does have to do with B. It has a little less to do with C, so we're going to have to calculate that as well in just a second. We had the vertical shift right there, and then we had our amplitude here, and I'm just kind of circling all of the important information so far. All right? Now, And again, this seems like a lot of work. I'm going through it a little slow. As you would get comfortable with this, this would actually be a pretty quick process. But the basic idea now is that we can go ahead and calculate one last thing, being the period. Now the period formula, you should know, period formula is just 2 pi over b. Okay. Well, 2 pi over b is just going to be 2 pi over 3, meaning that I now have a period, and let me just rewrite that since it's a little sloppy, of 2 pi over 3. Again, the period meaning that this is how long it will take to do one full cycle through my sine curve. Again, the nice thing about trig functions is the curves always look the same. They just have slightly different transformations. Now, one of the things is, I want to digress real quick, is I have a quick sketch here of the parent function of sine. And I wanted to identify a couple of things real quick. Okay? One of the big things that I wanted to identify more than anything else, okay, is that I wanted to identify the fact that if you take a look at these darkened dots here, okay, those represent important points. Now, this right here represents the middle of my sine curve. Okay? Here's the peak and here's the valley. Right? So in this particular case, I can see that that I'm basically cutting this into, and these aren't asymptotes, okay, but I'm basically cutting this into quarters. Because as it turns out, with every trig value, the quarters are going to be where you hit important points. So if we just graph those, we're going to be in pretty good shape. Okay? And that leads us to a new strategy that we can employ that will allow us to do these with relative ease. All right? Now, when I go to graph this, okay, all I am going to end up having to do is first, okay, comparing this to my parent function, okay, I can see that the parent function normally starts right here at 0, 0, and then it travels up to its peak in the first quarter, down to the middle in the second quarter, down to the bottom in the third quarter, and then it finishes up where it started. So I can expect the same idea. I just need to make sure that I account for the transformations in this particular graph. So in this graph, I'm going to go through the transformations here and realize that first I'm going to need to start, okay, with my shifts. So first I'm going to look at my phase shift here that told me that I'm going to go pi over 12 to the right. So if I just kind of make a mark here at pi over 12, okay, I know that that's where my graph will actually start. And then I have a vertical shift, I can see that up here, of 1. So instead of starting down here at 0, I'm going to start up at 1 instead. And now that is where my entire graph will start. Okay? Now, based off that, I can do the rest of the graph. What I'm going to do first, though, is I'm going to go ahead and say, well, I know that my period for this is 2 pi over 3. So if I'm starting, move this up a little bit, if I'm starting at pi over 12, and I want to travel 2 pi over 3, okay, well, then we can say that I'm simply going to go, well, I need to common denominator here, so we go pi over 12, and then this would be 8 pi over 12. So, plus, it's going to be 9 pi over 12, which you should hopefully notice is also equal to 3/4 of pi. So I can go ahead and on my graph here, just mark off that I'm going to go all the way out. If that's pi over 12, then if I want to go to 9 pi over 12, it's going to be about 9 of those, so I can just go maybe to about here. Okay? And that's 9 pi over 12, or just 3 pi over 4. And I know that this will be one full period. Now, as we noticed with our previous graphs, okay, we noticed that we cut this into quarters, and all of the important points happened at the quarters. And if you look, what that basically means is that if I cut it in half, and then I cut that in half, and then I cut the upper section in half, I'll divide it into quarters, and that should work well for graphing out my curve here. So I'm going to go ahead and do exactly what I was saying there. I'm going to cut this in half, okay? And then I'll cut it in half again. Okay? And I'll leave it to you to figure out how you can figure out what these values are in the middle here. All right? But if you have it graphed out like this, it should be pretty much a piece of cake from this point to figure out where to go with it. Now, based off this, I know that if this is my starting point, and with a sine curve I saw that this was the middle, I will travel 2 above this and 2 below this, depending on where I'm at in my curve. And I know that because my amplitude is 2, meaning that if I go from the middle, okay, to the top, it'll be 2. If I go from the middle to the bottom, it'll be 2. Now, the one other thing that I know is that my amplitude, or that my curve has to be flipped. So if I look back once again to my parent function, I can see that my curve generally goes up first to its peak. Now, since it is going to be flipped, it will do the opposite. So I'm going to travel down first, and then up, and then back to where I was. So I can graph out my points here, knowing that the first quarter, okay, I'm going to travel down to my lowest point, which is going to be 2 below the middle, okay? Or in other words, it'll just be right here at -1. I'll travel, in the next quarter, I'll travel back up to the middle. Okay? For the next quarter, I'll reach my peak. And then the last quarter, I'll end up where I started. Now, if I graph the curve, I just go from here, kind of try to make it nice and smooth, and we have a curve. And again, generally not going to be judged off of your artistic merit, but it needs to look fairly nice. All right, the one thing I did want to point out real quick is that all of these values, if you were using the tool or the chart that I had given you before, should look fairly familiar. And where the values come from, okay, just to point them out, this -2, we were multiplying times all of our y values. So that was the amplitude, and it took into account the flipping of the graph. Okay? So if you notice, if you check out the y values here, these are the same y values that we ended up with on our graph here. It just is slightly more organized. Now if you go and you want to find the phase shift, well, the phase shift is taken care of right here. Again, since we know that we're going to actually be inputting 3 times x minus pi over 4, we can set that equal to theta so that we know when our input will be equal to 0. And that actually works out to be more or less the phase shift. So the phase shift in this case was just pi over 4 times 1/3, which was pi over 12. And we have that right here. Okay? And then if you notice, you can also calculate the period here by just taking the last value, 9 pi over 12, and subtracting the first value in the new x value column. And if you take 9 pi over 12 minus pi over 12, you end up with 8 pi over 12, or what we found the period to be 2 pi over 3. Again, this is this tool is meant to organize everything that I did in this example. Okay. So you can feel free to continue to use it. You'll need to internalize it, as you can't use it on the test. But if you take a look at this method and you kind of work through it, you can see that it will eventually be a bit faster than this and a little less tedious.